Hello and welcome to section 3.2, Rolle's theorem and mean value theorem. In this section we're going to use the extrema that we were dealing with before to take it one step further and to show that there is at least one number where there is a max or a minimum. And so Rolle's theorem was looking at maximums and minimums, and Rolle was looking at trying to determine if you could find a max or a minimum of a function. And so what his theorem is all about is basically saying that if you can show that, and down here this is very important, that Rolle's theorem is an existence theorem. It doesn't prove that when you're using Rolle's theorem, you're not trying to prove that there's a value in there, what the value is. You don't try to prove what the value is with Rolle's theorem. You try to prove that there is a value there. And you're just trying to show that the value does exist. And then it takes more work to figure out, outside of Rolle's theorem, to show what the value is, where the maximum or minimum is. That's what we're really talking about. So Rolle's theorem basically says this: if you can show that by plugging in a into a function, plugging some number into a function and getting a y value, plugging b into the same function and getting the exact same y value as before, as you did when you plugged in a, then somewhere between a and b, the function had to turn back, if it was continuous, that you have a relative maximum or a relative minimum. And so what Rolle basically says, that if I can plug in a into my function and b into my function in this closed interval, then somewhere between a and b, if they are the same values, I end up with a horizontal tangent, or a place where the graph is a maximum or a minimum. And it would work also if there is no smooth curve where the derivative is equal to 0, where we come to a point where it's undefined also, but it will also work there as well. So Rolle's theorem is an existence theorem. It just shows that there is a possibility of it, and what it would take to take it that step further is just a little bit more work. So Rolle's theorem will help us determine whether there is going to be a horizontal tangent or a maximum or minimum in the function. So in this one it says, find the two x-intercepts, this is our example, of this function and show that f prime of c equals 0 at some point between the two intercepts. Okay, so basically what's happening here is, since they're saying they want the two x-intercepts, I'm just going to quickly sketch a graph. So say my graph looks something like this, and you can see that it's a parabola and it's going to open up, so it's going to do that. So we know that what we're looking for is the two x-intercepts. Well, in this case that means these guys, these x-intercepts, f of a is going to equal 0 and f of b is going to equal 0. Now they don't have to equal 0. It could have been somewhere up here that, you know, maybe this was f of c, some value equaled d equaled some number, and then over here that f of g, whatever, equaled the same value d. So it doesn't have to be that they equal 0, but in this example, since they're using the two x-intercepts, then if we can find two places where this graph is crossing the x-axis, then that would mean that this function is going to turn back on itself. So we're first going to find the x-intercepts, and how I would do that is by factoring. So remembering my algebra from before, that I have x squared minus 3x plus 2. The only factors of 2 are 2 and 1. And they both have to be negative because we have a negative 3 in there. So negative 2 and negative 1 added together give me negative 3, and negative 2 times negative 1 is positive 2, so it looks like I factored correctly. And so then these guys, my x-intercepts, are going to be x equals 2 and x equals 1. So this guy would be 1 over here, and this guy would be 2 for my x values. So my f of a is no longer a, it's going to be f of 1 will equal 0, and my b value over here is f of 2 equals 0. So now that I have two different x values plugged into my function, and they equal the same y values, now I can use Rolle's theorem to say that that basically says that some point between these guys there is an f prime of x equaling 0. So then it says, and show that f prime of 0 at some point between the two, that is at some point between these guys. So I'm going to take the derivative of this function, f prime of x, which will give me 2x minus 3 when I take the derivative. And if I set that equal to 0, because that's what we do, f prime of x equals 0, and solve for x, 2x minus 3 equals 0, add 3 and divide by 2, x equals 3/2, which is 1.5, so that's somewhere between 1 and 2. So there is my x value. That proves that in Rolle's theorem, that since I had two y values identical, that somewhere between those two, I ended up with a horizontal tangent. A horizontal tangent, a zero slope, a maximum or a minimum. And as you can see by my graph and knowing that transformations of graphs, that this thing has to be a minimum. But we could plug this 3/2 back in here and find out that it's the lowest value in the function also. That would help us. So then there's an extension to this Rolle's theorem is the mean value theorem. And the mean value theorem, the only difference between this and Rolle's theorem is that in the mean value theorem, we're saying that we can pick any slope. So we make a secant line. We just pick 2 points. They don't have to have the same y value. We find the slope of that secant line, and the mean value theorem says that we can find a tangent line that is parallel to the function. And so it doesn't matter anymore whether these guys are equal to 0. We're not going to find a horizontal tangent. We're just going to find a tangent that is parallel to it. So you can see that we take, it's basically, this is the secant line right here. This is the slope of the secant line. So slope of the secant line is this half, and then this is the slope of the tangent line. So slope of the tangent line is over here, and so that's really what we're looking at. Tangent line equals secant line in a closed interval. And so that's what mean value theorem is all about. And so then there's an alternate form for the mean value theorem. It looks something like this. Basically, if you looked at the other mean value theorem, let me back up a page here, where we had f prime of c, slope of the tangent line equal to the slope of the secant line, and they just solved this so that they could find one of the missing values, one of the y values if you didn't have it. If you knew the slope of the tangent line and you were looking for the y value that would give you, this is basically what is the y value that would give you a secant line that is parallel to the tangent line over here. And so that's really all they did, is they multiplied by b minus a, so f prime of c times b minus a will equal f of b minus f of a, and then they added f of a across the equal sign, so we got f of a plus f prime of c times b minus a equals f of b. So the reason they do this is just so that in case they ever ask you the question is, you know, what y value will give me a secant line that is parallel to the tangent line? Well, here's the alternate form, and that's really what we're looking at. And so this concludes our notes for this section. We'll talk more about this stuff. We'll have plenty of practice on it, but please come to class prepared to ask any questions about this.